Hello, we are discussing about GATE 2000 ECE paper, and this question is related to analog circuits. Introducing a resistor in the emitter of common emitter amplifier stabilizes the DC operating point against variations in A. Only the temperature, B. Only the beta of the transistor, C. Both temperature and beta, D. None of the above. So DC operating point will be stable against variations in temperature or beta or both, that you have to specify. Okay, so this is what the circuit we are going with. So let us assume we will see what is actually introducing a resistor at emitter. This is what common emitter amplifier. The first diagram, if you look at, this is the first one, let us assume A, and for this first diagram this is emitter and this is base, it is collector. So there is no resistor at the emitter, emitter is directly connected to ground. Okay, and if you introduce a resistor Re across emitter at that time, okay, which parameter, whether temperature or beta or both, will be stabilized. Okay, will be the effect of these things are going to be reduced, so this operating point is going to be stabilized. That is what we are going to calculate. Operating point, first of all you must know, operating point is also called as Q point. It is nothing but VCE comma IC. Operating point is nothing but VCE comma IC. Okay, so this value of VCE and IC should be constant irrespective of the variations in temperature and beta, whether it is happens with Re or not. Okay, that we will check. So we are interested in showing VCE and IC values are going to be constant. If IC changes, VCE changes. Okay, because VCE can be written as, VCE is nothing but V out in our case. V out is nothing but, in this case V out itself is nothing but VCE, and in this case V out is equal to VCE VCC, you can write VCC minus ICRC, which is nothing but VCE. And in this case also you can write the same equation as VCC minus ICRC. So if IC changes, definitely VCE changes, remember that one. VCE and VE is function of IC. So if IC changes, VCE changes. If IC constant, VCE constant, so that Q point is constant. That is what we are going to check. Okay, so now draw the Thevenin's equivalent of these diagrams. So Thevenin's equivalent of these diagrams are going to be looks like this one. So Thevenin's equivalent circuit for this first diagram, and it is RB, this is VB for example. Okay, and this is V0. We are not interested in that one, we are only interested in IC. Okay, now if you are going for this one, at that time the circuit is going to be having Thevenin's resistance, Thevenin's equivalent is in this way. There is a Thevenin's resistance and a Thevenin's voltage source at the base, and this is plus VCC, and it is RC, this is RE, and it is RB for example, this is VB, which is nothing but related to input signal. Okay, and now we will draw some voltage polarities. Current flowing through this one is nothing but IB, and current flowing through this one is IE, but it is approximately equal to IC only. Okay, and VBE is equal to, VBE is plus minus VBE, voltage drop across base emitter. Okay, now we are going with introducing with RE. If you write the KVL, okay, KVL across this one can be written as VB minus IBRB minus VBE minus ICRE is equal to 0. Instead of writing IERE, I am writing it as ICRE is equal to 0. From this one, IB is equal to, you can write it as, okay, VB minus VBE minus ICRE divided by RB. This is what you can write. This is important equation for us to verify the variations, to check about the variations. Okay, so now first I am going with temperature. So effect of temperature on Q point. Okay, so first of all we will see what happens if temperature increases. Okay, later I can go for the remedy with this circuit. So first thing is, first, as temperature increases, let us assume as temperature is going to be increases, whenever temperature increases, reverse saturation current IC0 is going to be increases. Reverse saturation current is due to minority carriers which only depends on temperature or other external energy excitation like light. Okay, so IC0 is going to be increases. Whenever IC0 increases, at that time IC increases. So collector current is going to be increases because IC is equal to beta times of, we know the equation of IC is equal to beta IB plus 1 plus beta times of IC0. This is what the general equation of collector current in common emitter mode. So from this one, if IC0 increases, IC is also increases. So whenever IC increases, at that time power dissipation is going to be increases. Power dissipation across the junction, across collector base junction is going to be increases. Whenever power dissipation increases, again temperature increases. Power dissipation is nothing but it is VCE multiplied by IC. So as IC increases, power dissipation is also increases. So again, since power dissipation is increasing, again temperature increases. And whenever temperature increases, IC increases, that is power dissipation increases, again temperature increases. Within no time the transistor gets breakdown. That is what generally we call it as thermal runaway. This situation is going to be called as thermal runaway situation. Okay, this can be avoided if you introduce a resistor RE at the emitter. Okay, how? We will see. As IC increases, okay, can we say that one, the voltage drop across this RE increases? So that voltage drop across that RE, that is IC into RE, is going to be increases. Okay, whenever IC into RE is going to be increases, at that time IB value, is it reduces or not? Is it reduces or not? So this will be reduces because IB is equal to, what we have written the equation, VB minus VBE minus ICRE by RB. VBE is constant, VBE is also constant, that is 0.7 volts for silicon transistor. And now numerator value minus ICRE, ICRE is going to be increasing. So you are reducing, that is numerator get reduces. Whenever numerator gets reduces, IB reduces. So this IB reduces. This is going to be making IC to reduce because IC is nothing but beta times of IB. Whenever temperature increases, that makes IC to increase, but the same increase in IC, that is making IB to reduce, so that IC is going to be reducing. So we can say that one, there is a stabilization is going to be taking. So from these two things we can say IC is almost stable. Almost stable. Whenever IC is stable, at that time VC is stable. So Q point is stable. So Q point is stable against the variations in temperature. Now we are going for the beta variations. Second case B. Okay, as beta increases, as beta is nothing but common emitter short circuit current gain. As beta increases for the given IB, okay, for as beta increases, IC increases for given IB. that is for the fixed IB, even though you are not changing the IB value, if beta increases, IC is going to be increases. Okay, and then whenever this is going to be taking place, at that time VCE is going to be reduces. VCE is going to be reduces, but okay, that is VCE is reduces, and if this is, if RE is not present at that time, this is going to be the situation. If RE is present at that time, IC increases. Whenever IC increases, again, okay, we are coming from this one. Instead of going in this way, so IC increases. So whenever IC increases at that time, that is going to be making IC into RE, this term is going to be increases. Whenever this term is going to be increases, IC value is going to be reduces, because this is making IB to reduce. This is making IB to reduce. Because of this one, IB reduces from this equation, so that IC reduces, and from this one we can say that one IC is going to be remains constant. IC is almost constant. IC is almost constant. So Q point is constant. So by introducing a resistor in emitter of common emitter amplifier, we can get the stabilization against the variations in temperature as well as beta. So the right answer for this question is both temperature and beta. DC operating point, that is Q point, is stabilized against the variations in both temperature and beta. Right option is C.